Hello everyone. In this video we'll talk about probabilities on operations and conditional events. As a reminder, so if we have an event A and you know that the probability of that event will be between 0 and 1, it's not possible to have a negative probability or a probability that is greater than 1. If we have an empty set, this is phi, then the probability is going to be equal to 0. Or if we have the complete sample space, of course the probability is equal to 1. If we have multiple events, A1, A2, and A3, and they are mutually exclusive, so the union is going to be just the sum of the individual probabilities. So let's check this additive rule in the cases where they are not mutually exclusive. So for instance, if we have two events A and B, and when we check the Venn diagram, please notice that there is some overlapping between the two events. So there is an intersection and it's not empty, A intersection B. Then if you want to compute the union of these two events, so that will be the probability of the first one, of A, plus probability of B, minus the intersection. So why we do minus the intersection? Because, for example, when we add probability of A, so we add this part that have moon one time, right? Then when we have, and this intersection is added once too, right? Because that's part of A. When we do probability of B, so we're adding the second circle, right? So that means that this area here, we're adding it one, but then the intersection part is being added twice because it's part of A, but it is also part of B. That's why then the third part of the equation is minus the intersection. So we remove it 1. So instead of 2 times here at the end, you end up with that area only 1 time. So when you have each of these areas only 1 time, that means that we're getting the whole thing complete, right? So that's how we get the probability of the union between two events, A and B. Let's check an example. So John is going to graduate from an industrial engineering department in a university by the end of the semester. After being interviewed at 2 companies he likes, he assesses that his probability of getting an offer from company A is 0.8 and his probability of getting an offer from company B is 0.6. If he believes that the probability that he will get offers from both companies is 0.5, what's the probability that he will get at least one offer from these 2 companies? Alright. So let's organize the information real quick. So we know that the probability of getting an offer from A is 0.8, right? Right here. Then the probability of getting an offer from company B is 0.6. So the question here is, what is the probability that we will get at least one offer from these 2 companies? So that's pretty much the union. Why the union? Because the union means the probability that A is going to happen, B is going to happen, or both are going to happen. That means that that's the probability that John's going to get an offer from company A, also an offer from company B, or both of them at the same time. So those are the scenarios that are considered by this operation, by the union. Then, according to the previous equation, this is probability of A plus probability of B minus the intersection, which we know, right? Because John believes that the probability that he will get offers from both companies at the same time, that's 0.5. I forgot to add it here. A intersection B, that probability is 0.5. Therefore, when we complete the equation, now let's plug in the numbers. So it's 0.8 plus 0.6 minus the intersection, that's 0.5, right? So we get that the probability that he will get one offer from one company or the other, or both of them at the same time, is equal to 0.9. So that was using the rule that we discovered for the additive rule of 2 events. Let's check a second example. So what is the probability of getting a total of 7 or 11 when a pair of first dice is tossed? So here we want to compute one or the other, right, or both. So that's union again. So this is A union B. That's the question here in this problem, right? So the first thing that you need to do is, okay, so let's find the probabilities for these events. So A, when A is gonna happen, the event A means getting a total of 7. So let's find what are the sample points in which we will get as a result a 7. So that's when you get the 3 4 or 4 3, when you have 5 2 or 2 5, and finally you have 6 1 or 1 6. So we have 1 2 3 4 5 6 sample points that will satisfy that condition, right? So we can compute the probability of A right away. Probability of A is 6 over 36, right? 6 sample points out of 36, that's the total. Then for event B, there is a similar calculation. So if we want to compute B, remember it's when we get the number 11, but there are only 2 sample points, right? That will be 6 5 and 5 6. Those are the only 2 options in which the sum of the dice will be equal to 11. Therefore the probability is equal to 2 over 36, right? That's 1/18. Then when we do the union, probability of A union B, that will be the sum of the probability of A and B. So that's 6 divided by 36, that's 1/6, right? Plus 1/18. And now we need to remove the intersection. But if you notice, the intersection of A and B, it's empty, right? There is no intersection. They don't have common sample points, right? Therefore, you need to remove anything. So just minus 0. I will just write it down for you as a reference. Therefore, you can compute the union of these 2 events. That will be 2 9s. And that's the solution of this example. Alright, so what if we increase the number of events, let's say 3? So the union of A, B, and C. So that's the probability of A plus probability of B plus probability of C minus the intersection of A and B minus the intersection of A and C minus the intersection of B and C, and then this is a little bit tricky, like why it's plus the probability of A intersection B intersection C. So let's check that real quick, and this is why the Venn diagrams are really useful. So let's say that we have A, we have B, and then we have C. So when we add them, A, B, and C, the probabilities, so we're adding this region ones. Be careful with intersections, right? Because here, this intersection between A and B, so this area has been added twice. This is because it belongs to A and belongs to B, right? But be careful because here in the triple intersection, we have A, B, and C. So this one is being added 3 times, right? The intersection between A and C, one part is 2, but the other one is 3, the triple intersection. And between B and C, this section, it's 2 times, right? But the triple intersection again is 3. All right. So the ones, at the end, we only want the number 1 in each region. So that's why we start removing. So the first removal, it's A intersection B. So if we do A intersection B, we're removing intersection B. This one is going to be 1. I need a smaller eraser. Okay, let's see if this make it. Alright, so instead of 2 we have 1, and instead of 3 we have 2. So this is 1, and this one is 2, right? Because we're removing A intersection B. Then, when we remove A intersection C, then that's going to affect, this one is going to be 1, right? Instead of 2, and this 2 is going to be 1, 2. So let me add the ones. So 1, 1. And the last one, when we remove B intersection C, therefore the 2 that we have will be 1, but this 1 is going to be equal to 0, and that's a problem, right? So this is going to be 1, and this is going to be 0. Why it's a problem? Because we want every single region to be added one time, right? Therefore, that's why we have plus the triple intersection. So instead of 0, we go back to the number 1. And that's it. So that's why the equation works, right? We add the product of the 3 events, then we remove the intersections of each pair, and at the end we add the triple intersection. Okay, let's keep practicing some of these operations that we have seen. The probability that an American industry will locate in Shanghai, in China, is 0.7. The probability that they will locate in Beijing, China, is 0.4. And the probability that they will locate in either Shanghai or China, or both, that's the union, right? One, the other one, or both, that's the union, is 0.8. So what's the probability that the industry will locate A in both cities, B in either city? So let's organize the information real quick. So probability that the company will open in Shanghai, it's 0.7. Probability that will open in Beijing, it is 0.4. And the union, Shanghai, Beijing, or both, that's 0.8. As union B, that's 0.8, right? Then the first question is, what's the probability that the industry will locate in both cities at the same time? So the 2 events occurring at the same time. That's an AND, that's an intersection. So for A, we're going to compute the probability of S intersection B. Since we have the union, then guys, we can solve it real quick, because remember that in the equation of the union, you have the intersection, and you already know the value of the union, so you can just solve for the intersection, and that will be the probability of S intersection B is going to be equal to probability of S plus probability of B minus the union. So I'm just, again, the original equation was the other way, you know, like was for the union, but you can just solve it for the intersection. It's the same thing, of course. Since we know every single value here, you know, probability of Shanghai, opening in Shanghai, opening in Beijing, and opening in both, or in only one of them, that's the union, then we can find the probability, right? You just plug in the numbers, and you get that intersection, it's equal to 0.3. That's 0.7 plus 0.4 minus 0.8. That's how you get the 0.3. All right, that was part A. Let me add one page real quick here to compute part B. All right, so in part B is that what is the probability that the industry will locate in either city? That means that it won't open in Shanghai and it won't open in Beijing. So we're being asked in part B, this B, the probability of S complement. That means that the company is not open in Shanghai and that the company is not going to open in Beijing. So here you have like different ways to solve it. So you can try to write down the expression as we did for the first one. right? But the problem is since it has the complement, that's the prime means, or you can add a bar on top of each letter, you will need to figure out some of the expressions. The complements are easy, but maybe the union or intersection of the complements, those are the tricky one. An alternative way, guys, to solve this problem is to use the Venn diagrams. They are really helpful because you can derive some expressions only by looking at them. So let's try to see if we can get some knowledge of what is S complement intersection B complement. Let's see what is the meaning of that expression. So we check S and B, right? We know that there is some overlapping because the intersection is not empty. There is some overlapping, right? Okay, so what is S complement intersection B complement? So S complement, it's everything that is outside S, everything outside S, right? But then intersection B, what is B complement? Everything that is outside B. That means that the intersection between those complements will be everything in the rectangle except the two circles. It's everything in the rectangle except the two circles in the middle. Remember that the whole rectangle represents the sample space. That's the probability is equal to 1, the whole thing, right? But we need to remove this area, right? The two circles. So what is that? Remember, that's the union. That's the union. The two circles together, that's the union, right? Because it includes the probability of S plus the probability of B and includes the intersection, the overlapping. So one or the other one or both of them, right? That's the union. So this expression is equivalent to everything, the whole rectangle, the whole sample space, minus the two circles together. So that's minus the probability of S union B. Because the two circles together, again, it's one or the other one or both of them, right? That's the union. And it makes sense if you think about it, because here is that you won't open in Shanghai and you won't open in Beijing. But in this one, in the union, you have that you open in Shanghai, or you open in Beijing, or you open in both. So what's the complement of that? The complement means that you won't open in the two places at the same time. So it makes sense. It makes sense. Then using this expression, this is just 1 minus 0.8. So the probability that the company won't open in Beijing and in Shanghai, that will be 0.2. That was the desired probability in this example. Okay, let's keep going. Conditional probabilities. Sometimes when you get some piece of information, that means that you know that an event has occurred, you can update your probabilities. So this is the notation that we're going to use. Probability of B given A. This is not B over A, it's B given A. So what is the meaning of this? This is what is the probability of that event B is going to occur given that we know that event A has already occurred. So it's like, okay, I want to update the probability given that I know that event A has occurred. So what is the impact of that? There is an equation to update the probabilities and to compute the conditional probabilities. So the probability of B given A, it's equal to the intersection of the two events. So that's probability of A intersection B divided by the probability of A, or in general divided by the probability of the event that has already occurred, right? Again, B given A, it's equal to the probability of the intersection of both. Here the order doesn't matter. In the intersection, the order doesn't matter. In the conditional, the order, it's important, it matters. In the conditional, it matters, but in the intersection, it doesn't matter. All right, so you will always divide over the probability of the event that has already occurred, the one that is given, right? The one that is located here. Okay, so let's check some examples to practice this conditional probability. This is just to give you some intuition, this first example. It says, the probability of getting a 1 when rolling a die, imagine that getting a 1 it's event A, getting a 1. So the probability of A is 1/6, right? If you don't know like any other information, because you know that you have 6 possible outcomes, and only in one of those outcomes you get 1, therefore the probability is 1/6, right? But then let's say that we define an additional event, let's call it B, that an odd number is observed. That's the event, an odd number is observed. So if you know that an odd number is observed, that means that the outcome can be either 1, 3, or 5, right? So if you know that, again, if you know that an event B has occurred, for example, that an odd number has occurred, that means that there are only 3 options and not the original 6 options. Why? Because you know that the outcome is an odd number. So it might be number 1, 3, and 5. So we discard 2, 4, 6 because those are not odd numbers. Then if we want to find the conditional probability of event A given B, in this case, this means the probability of getting the number 1, given event B, that which means that an odd number was observed. So an odd number means that the possible outcomes are 1, 3, and 5. Then the probability here is going to be equal to 1/3, right? Because there are 3 points, right? And the point that will give you the 1 is only 1, so 1/3. So please notice the difference between the probability of A that we had originally was equal to 1/6 versus the probability of A given B. In A, we don't have prior information. Probability of only A is 1/6 because we don't know about any other events. But in the conditional probability here, you know that B has occurred. You know that the outcome, in this case, it's an odd number. That means either 1, 3, or 5 were observed. Therefore, the probability of getting a 1 is 1/3, right? So this is like the intuition of how the conditional probability works. It updates your information. So how the occurrence of an event is affected by the occurrence of a previous event. All right, let's check this an easy example. So suppose that the sample space is the population of adults in a small town who have completed the requirements for a college degree. So they are categorized according to gender and employment status. So we have female and male, employed and unemployed. The data, so it's presented in the table. Now, 2 events are defined. The first one is M, a man is chosen, and the second one, E, the one chosen is employed, right? And then we are asked, okay, let's find the probability of a man is chosen given that the person is employed. That's the question here, right? A man is chosen given that the person is employed. So if we use the equation, that will be the probability of M intersection E, the 2 events happening at the same time, divided by the probability of the previous event, right? The event that is known. So the person is employed. So let's find those probabilities. The first one, M and E, the person chosen is a man, and the person is employed. So the 2 events happen at the same time. So that will be 460, right? This is the intersection of male and employed. So that occurs in 460 out of the total, right? Out of the 900. So the probability will be 460 divided by 900, that intersection. And the probability of employed is how many people we have employed, 600, divided by the total, that's the 900. So 600 divided by 900. So that will give you the probability, that the probability is 460 over 600. And of course, you can, like cancel some zeros and all that stuff. Other way to kind of like solve this problem faster is that if you go to a table and you want to find the probability that the person is male given that the person is employed, so you know this piece of information, then you go right to the 460. So probability person is male, given that it's employed, so it's going to be equal to the 460 men employed over the total number of employed. And of course you get the same result in that case. Let's now practice this is going to be the last problem in this video. The probability that a regularly scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.82, and the probability that it departs and arrives on time, the intersection is 0.78. And then we are being asked about some probabilities. So let me add an additional page here. Alright, so we can organize the information real quick. Probability of D it's 0.83. Probability of A it's 0.82. And of course the intersection. The intersection A or A intersection D is the same. In the intersection the order doesn't matter. Same thing in the union. The order doesn't matter. The order matters in the conditional. This is 0.78. Alright. Then let's get started with the first one. Let's find A. What's the it says arrives on time, given, that's a conditional probability right there, that it departed on time. So what's the probability that the person arrives on time, given that it departed on time? So usually the probability of arriving on time is 0.82. So let's see what happened if we know that that new piece of information, that the plane has departed on time. So let's use the equation, right? The intersection A intersection D, or the intersection A is the same, divided by the probability of the event that is known, right? The one that has occurred, probability of D. Then this information is 0.78 divided by probability of D, it's 0.83. So the resulting probability is 0.94. So this is interesting, right? Because the probability of arriving on time is just 0.82. But why now the probability of arriving on time is 0.94? So the probability is increasing given this piece of information, right? Because if you know that the plane has departed on time, then of course that will increase the probabilities of that the plane is going to arrive on time. So it makes sense that the probability is going up. It makes sense. Let's solve now part B. It says departed on time, given that it has arrived on time. So it is the opposite. So probability that it departed on time, given that it has arrived on time. So we expect something similar, right? That this probability, this conditional probability, is going to be a little bit higher than the probability of departing on time, because you know that it arrives on time. So it will increase the probability of departing on time. Then we use the same equation, probability of A intersection D, or the intersection A, doesn't matter, divided by the probability of the previous event, or the one that is known, probability of A. So we get 0.78 over 0.82, and we get that the probability of departing on time, given that the plane has arrived on time, is 0.95. So again, it increases compared to original probability, given that new piece of information. And let's check part C. The plane arrives on time, given that it did not depart on time. So that's the probability of A arrives on time, given that it did not depart on time. That's the complement of D, right? That's the complement of D, because it didn't depart on time. That's a conditional probability using a complement. So the way to find this is the probability of A intersection D complement, which we don't know yet. We don't know this intersection yet, over the probability of D complement. We know D complement, right? Because if you know D, D complement is 1 minus the probability of D, right? Same thing with A complement if needed. You know it. All right. So here, what we can do is that we can try to use the Venn diagram. The Venn diagram might help us to identify how to compute that probability. So let's try to use it. So we have A and D. A, so A is the circle, right? Intersection. Oh, I'm sorry, this is D. This is not B, it's D, right? The part. All right, so the intersection of A and D complement. So the complement, because that's what we're trying to find this expression, the complement, it's everything outside D, right? And the intersection with A, then that will leave us this expression, right? That's like A, probability of A, minus the intersection of A and D. So again, this probability here, A intersection D complement, is going to be equivalent to the probability of A minus the probability of the intersection of A and D. Then we can replace that expression. So there will be probability of A minus probability of A intersection D. The nice thing about this is that we know these two probabilities, right? They are known. Then it will be easy for us to compute the expression. So now we get the numbers. So this is 0.82 minus 0.78 divided by the complement. We know the probability of D is 0.83, then the complement is 0.17, right? 1 minus 0.17. So we compute the probability. So you will get that the probability of A, so arriving on time, given that it departed on time or it departed late, right? It didn't depart on time. That's the complement. It's going to be equal to 0.24. So it makes sense, right? If the plane departs late, if it does not depart on time, then that's going to affect the probability of arriving on time. Because remember, the probability of arriving on time originally was 0.82. But if you know that the plane has departed late, then of course that will hurt the chances that the plane is gonna arrive on time. Okay guys, that was everything about conditional probabilities. In the next video we will talk about independent probabilities. I'll see you later.